Hey everyone, Isaac here. I'm with Guillermo as well, and we're here to make a quantum algorithms tier list.
What is an algorithm, Isaac?
So I guess the dictionary definition of it, aka what's on Wikipedia. In quantum computing, a quantum algorithm is an algorithm which runs on a realistic model of quantum computation, the most commonly used model being the quantum circuit model of computation. So basically we're looking for anything that can run on a quantum circuit, basically, right? I think that's pretty much it. So another thing too is there's tons of quantum algorithms in existence, specific ones with specific tasks they do or things that they're good at. And usually those things fall under a bigger umbrella or a bigger category, a broader category of quantum algorithms. So we're not going to categorize each specific algorithm. We'd be here for days. So for instance, what I mean is VQE, QAOA, they're both good examples of variational quantum algorithms. Okay, so we have some broader algorithm categories that we're going to assign tier values to. The first one we have is variational quantum algorithms. Then we have quantum phase estimation, the quantum Fourier transform, linear combinations of unitaries, quantum singular value transforms, QSVT.
All
right. How do you pronounce? Is it Mottonen? Mottonen?
I used to say Mottoten, so probably
Mottoten.
It's not correct.
Okay, so Mottonen. Excuse me if I'm butchering your name. This is somebody's name. It's a state preparation routine. Qubitization, amplitude amplification, QROM, and the Hadamard test. And you might be wondering here too, there might be some categories you think are missing, or maybe we've gone too specific and there are some overlaps, right? There's going to be some gray areas, but we consulted knowledgeable people here at Xanadu about what to put here. So this is kind of what we came up with. And hopefully this doesn't stir up too much controversy, but it probably will anyway. We have three sort of criteria we're looking at. How useful are the algorithms in the real world? So their applicability, that's probably the one we'll give the most weight to. How simple are they to understand? And then how easy are they to implement on hardware? So does the algorithm require a big circuit? Does it scale poorly? Lots of gates, lots of qubits, etc. That one also probably not given as much weight, say, as how useful are they in the real world. What's the saying? Necessity spawns creativity or whatever. Basically, if an algorithm's super useful but it's kind of hard to implement on hardware, we'd probably figure out how to do it. There'd be somebody would make a large enough quantum computer and we'd figure it out, I think. We have 4 categories. C all the way up to 100% will change the world. I guess we'll get started.
Yes, get on with it!
Let's do it. Okay, so we're going to start with variational quantum algorithms. My definition of a variational quantum algorithm is given some objective function that you want to find the minimum of. You construct a trainable quantum circuit, which is an ansatz, to find the optimum value of the objective function. So it's literally just an optimization problem where the optimization or the thing you're optimizing is a quantum circuit, basically.
I will say there, the parameters are going to be part of the circuit in rotations and stuff.
Yep. QAOA, VQE, all those algorithms are extremely versatile, usually hardware compatible as well. Maybe not better than classical variational algorithms in some case. There's a kind of a misconception that quantum machine learning algorithms are just going to be better than classical ones. I don't know if you agree with that.
In these particular examples, used to be really difficult to test if something is going to be quantum advantage or not, because it could depend, I don't know, in quantum machine learning of the dataset you are working with, so it's a lot of promise, like you say.
Yeah. There's no doubt that this is kind of useful. I don't know, what are you thinking? I don't think this should be C tier. I don't think it's at the bottom, but I'm kind of between B and A a little bit. I don't know if you think it should be in B or A.
I mean, this variational algorithm, the application is super clear, and normally it's one of the main issues of another quantum algorithms. Here you are going to have hundreds of different examples. So that's a good point.
Yeah. So the applicability part is definitely there. I would say they're also relatively easy to understand compared to some of these here. Like the concept of a variational algorithm is quite simple.
Yeah, I would say people that come from the classical world in machine learning can easily understand the idea.
So are we thinking A then?
Yeah, I would say
tier? Okay, A tier? Okay, I don't disagree with that. Next one up is quantum phase estimation.
From the mathematical point of view, quantum phase estimation is an algorithm that, well, you have a matrix or an operator, you have an eigenvector, and your goal is to find the eigenvalue of this eigenvector. And this seems like very difficult to understand maybe, but has a lot of different applications like quantum chemistry, these optimization problems like the travel salesman. I really like this algorithm, I have to say.
One of the researchers here at Xanadu, he always says that if you're going to teach anyone one quantum algorithm, it should be quantum phase estimation, or at least he's said that before. I don't know if he still thinks that, but I know he has said that once. It is kind of spooky. It's one of those cool algorithms that's like, seems like, how is this possible?
Maybe you know the HHL algorithm to solve linear equations. So it's based on quantum phase estimation or period finding. It's important. Maybe 100% is too much.
Yeah.
I like A.
I think we need to be careful. We can't put all these algorithms in A. Looking at the rest here, I think there will be things that aren't A tier algorithms for me. So I'm okay with putting this in A, honestly. Now, would you put it above variational quantum algorithms or below it?
I didn't know there was an order here. Let's put it after that. After? Yeah.
All right, quantum phase estimation. Next one we have is the quantum Fourier transform. Classical Fourier transforms, the algorithm is essentially you can write any function as a linear combination of complex exponentials. That has lots of applications in signal processing. That's probably the biggest one is signal processing. So it's just classical Fourier transforms are like extremely useful. They're used everywhere. Probably how you're watching this video right now, there's some Fourier transform going on. It's used everywhere, and what quantum Fourier transforms, I mean, we can go into the details of the algorithm, but basically anything that you could do with a classical Fourier transform, you could do with a quantum Fourier transform. But the quantum Fourier transform is like that much faster. A lot of algorithms that you've probably heard of, like Deutsch-Jozsa, Grover's algorithm, Bernstein-Vazirani, all those algorithms are basically branches of the quantum Fourier transform. There's also quantum arithmetic too, like quantum.
Quantum arithmetic, that's very important also. I like this intuition of change from time domain to frequency domain. That at the end is, for example, in this period finding algorithm is the reason why we use quantum phase estimation. We are able to generate like a wave function that is a periodic weight function. So just applying quantum Fourier transform, we can get this frequency and get information from there.
I think quantum Fourier transforms will 100% change the world. I don't know about you.
Well, it's tricky because we really like quantum phase estimation, and QFT, quantum Fourier transform, is a piece of quantum phase estimation. So without quantum Fourier transform, we couldn't do quantum phase estimation. 100% will change the world.
100%.
Yeah, so
don't doubt it.
So I'm thinking if quantum phase estimation should decrease to B, because actually the power.
Ooh, okay, maybe we can leave that. If A is becoming too populated, we can bump quantum phase estimation down to B.
Okay.
How about that? Linear combinations of unitaries. This algorithm basically lets you apply a linear combination of unitaries to some state. Obviously, it's built into the actual name of the algorithm, of course. When you apply a gate to some quantum state, the gate has to be unitary. When you add a bunch of unitaries together, that entity isn't necessarily unitary anymore. Like a Hamiltonian is a linear combination of unitaries. And if you wanted to model the application of a Hamiltonian onto some quantum state, you need to devise some way to do that on a quantum circuit. And that's what linear combination of unitaries does. Some algorithms here actually use it too, right? Qubitization kind of uses it.
QSVT can be used also. The QROM, maybe some parts of LCU.
Sure. Linear combinations of unitaries let you do Hamiltonian simulation differently and more efficiently, actually. So you could take like the Taylor series expansion of e to the IH, which is then just a linear combination of unitaries at the end of the day. And you could model that on a quantum circuit and it's a little bit better. We have some resources for all of these algorithms actually in the description below, and we have a good codebook node on linear combination of unitaries. I'll put that there.
Yeah, actually, for me, it was a very good revelation to see this algorithm, because when you learn quantum computing, you know that put one gate and another gate is always multiply them. But users always ask, oh, and how can add them? And we always answer, it's not possible because this unitary thing. But now the answer is no. We have an algorithm.
Yeah.
And this is LCU.
Yeah. Within, as of recording, like the newer versions of PennyLane have like built-in operations or operators for doing linear combinations of unitaries. So you can check those out, put those in the description too. Part of the algorithm is that you have some, auxiliary register and you have to measure like the algorithm is only useful if you measure 0 on that register. So there's some like me, I'm still tempted to put this in A, and actually what you said about quantum phase estimation, maybe we should put it in B. I don't know what you're thinking.
Yeah, I don't think it's an A. What you just say is a big deal. I mean, we can apply this addition, but it's not always guaranteed that we are going to have the good result. At most, a B.
At most a B, okay.
Yeah.
The first entry to B. I'm okay with that. I think I'm okay with that.
And I like it. I like the algorithm, but I will say in context, a B is...
Yeah, no, it's not bad. QSVT.
In the algorithm QSVT, what it's able to do is apply a polynomial to the eigenvalues of a matrix. So we have a matrix, we want to apply any transformation, so we can do it through this algorithm.
Probably most people who are watching this have done a singular value decomposition before, maybe in school, and you know that it's a very tedious task. And it's like ubiquitous. It's everywhere. You do it all the time, usually computationally now. You don't do it by hand except to just like learn the process of doing it. I haven't done a singular value decomposition by hand in like a long time. I don't know about you. It's probably been since I've been in school.
In the university, I remember, was not this.
Yeah. You don't have to do this singular value decomposition to transform things. You just do this quantum algorithm and you can apply any polynomial transformation to them.
One really cool application that is one of the last demos that we have is get the inverse of a matrix. Because we know that the inverse of a matrix is just to invert the eigenvalues. So if you are able to perform that transformation, you already have it.
We have a demo on QSVT, so you should go check that out. We'll put that in the description. Right, and the number of operations to perform this polynomial, it grows linearly with the degree of the polynomial, so it scales really well. So it scales really well. I'm thinking, and it's really not that bad to understand either. I think it's not as powerful as the quantum Fourier transform, but I'm at least prepared to put it right below it, or maybe in front of variational quantum algorithms.
There is also some things to take in account, like you are going to need to find some parameters to be able to apply any polynomial.
Right.
So there is a process that, or maybe you have to train or you have to do the maths to find that parameters.
Okay.
So there is still a bit of work there.
So maybe above variational quantum algorithms?
Maybe just before quantum phase estimation.
Right here, in between.
Yeah.
Okay. The next one is Mottonen. Mottonen. We'll put the paper to where the algorithm was originally formalized. Put that in the description. You can go read it if you want. It's kind of complicated, and honestly, all you need to know about it is that if you have some arbitrary state, some quantum state that you want to prepare, you basically just feed it to this algorithm and it'll just give you all the gates that you need to apply to some initial state, like an all zero state or something, to get the state you want. It's useful from that point of view, just straight up, like state preparation is the start of every quantum circuit. So it's really, really useful. I'm not sure how stoked I am. Like if you go read the paper, it's quite complicated, at least to me. The operations that it supplies to get some target state that you want, they're usually, I think they're all controlled rotation gates. So from that point of view too, those are hard to implement on hardware. I'm not super stoked on this one, but it is really useful. If you're ever in doubt about how to prepare some quantum state, like this is it. I'm prepared to put this in C or low B.
Wow.
I don't know, I'm not too stoked on it.
Yeah. I mean, it's super important to know how to prepare an algorithm and a state. And actually, know that we can do it. Of all the algorithms that we just see, probably this is the most C
Sure.
algorithm.
Are we putting it in C? I think so. I think so.
But it doesn't mean that there is a better algorithm
Right.
that we can use. So it's in C, but we are going to need to use it there. You have the template in PennyLane.
Yeah, there is a Mottonen state preparation operator in PennyLane that you can use. Okay, on to the next one, Qubitization. We have a codebook node about Qubitization. You can go check it out. Myself and David Wakeham, we kind of co-authored that one. It was a journey for me to understand. It's got bits and pieces of Grover's algorithm, linear combination and unitaries. We couldn't explain it in the time here, but basically what it's a form of Hamiltonian simulation. I feel like it's one of those algorithms that I feel like should be higher, but there's something about it just purely from how difficult it is for me to understand that's putting it lower. I don't know what your thoughts are.
Sounds good to me.
B?
Yeah.
Now, does it go above linear combination and unitaries, or okay? No. I'm going to put it below
No,
because
for
it
sure.
uses LCU. So I guess it draws some inspiration from it. But we're going to move on though, just in the interest of time. Okay, so amplitude amplification algorithms. Guillermo's a little biased. I think these are your favorite types of algorithms, right?
I love that. Okay, amplitude amplification is one of those algorithms, like Grover is in this family, to perform search in unstructured data. So you have an oracle. Is an oracle algorithm that is able to mark an element that you are looking for. So amplitude amplification try to increase the chance to actually get that mark state.
Are there any other notable shout out algorithms that we should be doing for amplification?
Yeah.
There's Grover's algorithm.
Grover's algorithms is the one that is easy to understand, but the generalization is called the Brassard algorithm.
Right, okay.
That actually is one of my favorite papers, because when you read it, you can see Grover say that idea, but we say it before. So it's trying to punch hey,
I see.
It's a good algorithm, but
I'm definitely thinking this goes in A. I don't know if it goes into 100% will change the world.
from the understanding point of view, is one of the not too many algorithms that actually you can understand with a picture. Like you can, this state go here. So this is something that we didn't say is the complexity of the algorithm.
Right.
In that case, these algorithms just achieve a quadratic speedup.
Yeah, it's not like exponential or
It's
anything.
not exponential.
Yeah,
So
true,
that
okay.
will be called something that, maybe. I'm
Does
biased,
this-
I really like this
I
algorithm.
know. Okay, so if we're gonna put it in A, where does it go in A? Does it go above QSVT? Does it go below it? For me, I think I'm putting it right between QSVT and quantum phase estimation. I don't know.
Makes sense. Actually, there is a paper that presents QSVT when they defend that QSVT could be used also for search algorithms.
Oh, I see. Okay, so I'm maybe gonna put it just below it.
Yeah.
Yeah. Oh, whoopsies. Other way.
I
There we
think
go.
makes sense.
Okay, QROM. If I have a database and I want the 22nd entry in the database, this algorithm will put the contents of the 22nd entry of the database in my main register. So it's basically like a database lookup.
Yeah, for example, these kind of algorithms used to be, let's try to search for one particular item of our dataset. So maybe we can apply Grover, but normally this is like the typical application that people think about, don't used to be really useful because the complexity to build a QROM used to be linear. So you are not going to perform a quadratic speedup if just load the data is linear. So it's not easy to find a real application when you are thinking in a database. The concept is good. The concept of we need to store in one auxiliary qubit the data associated with this index.
Right.
But the current scalability is not really good. So if in the future we solve that problem, it's going to be super useful. I will put in C.
Okay.
Let's put it there.
Right here, above Mottonen. I don't know. I think state preparation is just so quintessential. I think I'd put it below it. It's one of those things where it's just like, if that's the be all end all state preparation algorithm, we'll find a way to make it work. You know what I mean? Necessity creates invention, or whatever the saying is.
Yeah.
Okay, we have one more, which is the Hadamard test. It's a way to estimate expectation values. It's a really simple circuit. It's literally like probably one of the simplest, if not the simplest algorithm on here. Would you agree?
Yeah, I think so.
So yeah, I'll put the circuit on the screen right now. It's like literally a Hadamard, a controlled unitary, and the unitary that is controlled, it's the thing you want the expectation value of. And then the state in the main register is the state you take the expectation value with respect to. And then just one more Hadamard, and then you measure the auxiliary register. It's easy to implement on hardware, I would think. At least it seems pretty easy to implement on hardware, depending on like the unitary that's being controlled.
I like that also. This algorithm, like the inspiration for another algorithm. I'm sure quantum phase estimation was based.
I think this should probably go in at least A tier.
I was thinking like in the first position in B.
Oh, okay. In a lot of these algorithms that we have in A or 100% will change the world, the measurements as part of the algorithm, they're not measurements that are like expectation value of some operator or whatever. They're just like measure in the computational basis, like, you know, just do like a poly-Z measurement basically. What I think is cool about it is like it offers you a very simple way to get a measurement of an operator that may otherwise be complicated to measure, actually. So yeah, I mean,
but that particular task, maybe we have more algorithms to get the expectation value. It's not like this
It's not the only
main
one.
key that if there was not for the Hadamard test, we shouldn't build a quantum computer.
Yeah, whereas these algorithms here, like they're pretty quintessential. Yeah, okay. So where do you think it should go in B then?
First or second, I will say.
I'm gonna put it here. I'm gonna put it here. That is the tier list. I don't know how you feel about it. Do you want to change anything around? There's only one thing we said will 100% change the world. Is there anything in A that you want to move up to that?
Variational quantum algorithms is many things.
Yeah.
And I'm sure there is something there that can change the world, but there is a lot of things that not. So it's a difficult.
Yeah, and maybe with like all the large language models too, like there will be like a quantum one that was just like, you know, far superior than. How do you feel looking at that now that it's up there?
It's different, right?
Yeah. I'm okay with this. It's got to be one. You know, it's just like there's got to be at least one other planet in the universe that has life on it, right? There's got to be one. So
we're going to find it, right?
We're gonna find it.
That's perfect.
All right. So are we locking in the lyrics here? We're saving it. Save it. Title of tier list: the 100% accurate quantum algo tier list by Guillermo and Isaac.
Nice.
Save.
We did it.
So you can go check this out. If you like it, you can share it on Twitter. You can, you know, say, you know, give it a happy face, give it a poop emoji or something. I don't know. You can have fun with this. You can create this tier list again and like do your own tier list. Tag us on Twitter at PennyLane AI or on LinkedIn with your tier list. What do you think? Are we out of our minds? All right, that'll do it for this video. Please subscribe if you haven't already. Give this video a like if you liked it. Thank you, Guillermo, for joining me. And yeah, we'll see you in the next one. Ciao.
Thanks for watching.
Most quantum machining. What?
Should we watch there or the computer or?
Kind of quirky.
Seems like the news.
Yeah, that went okay.